Hey everyone, so this is the very last topic that we're going to cover, which is all about angular momentum. This is the very last thing to talk about in the AP physics stuff. So again, we've so far talked about angular kinematics. We went to angular forces, then angular energy, and then the last one is angular momentum. This is by far probably one of the more important aspects to keep in mind, even though this is probably going to be the shortest to go over, mainly because it works exactly the same way as linear momentum. So there's really nothing crazy, and it kind of follows a lot of the same rules that we've done before. So just like before, we have angular momentum, which is represented by a what makes the most sense, an L, and the equation is given by I omega. Why? Because remember, the linear momentum is mv. So replace mass with I, replace v with omega, and there we go. We have our new equation. Yay! Everything else ends up being pretty much the same. There are a few things that you need to realize. Like, for example, we know about linear momentum is conserved in the presence of an outside force. So in the absence of an outside force. So as long as we don't have an outside force or any external forces, the momentum of a system should remain the same, right? So if we have two objects colliding on a flat horizontal track where there's no forces of friction, no external forces of gravity that are going to make it go down because it's perfectly horizontal, the momentum of the system of the two cars crashing should remain constant or conserved. The same thing's going to apply here, except we're going to have to obviously remove the word force with the word torque. So in the absence of an outside torque, the angular momentum is always conserved. Like I said, just like the linear momentum. And the other really major thing to keep in mind about angular momentum is that it's the reason why planets travel faster as they get closer to the sun, and they go slower as they get further away. Now, I mentioned this before when we talked about it in energy, that you could think of this in terms of energy, and it does work. That when the planets are further away, they have more gravitational potential. As they get closer, that they lose that gravitational potential and it turns into kinetic energy, and that's why they go faster. And that is perfectly okay. However, it just happens to be a very common question for the AP where they start asking questions about why planets travel faster. And typically, the choice that uses the term energy will have something wrong with it that you may not notice right off the bat, but there's something about it that they're saying. Like they might say it's conservation of kinetic energy or something. They'll throw something in there to make the energy answer the incorrect one. And in those cases, uh, when they say anything about angular momentum, it's almost like 90% time the correct answer. So that's why I really want to stress this, that when you start seeing, why do planets travel faster as they get closer to the sun, it's because of angular momentum. Right? It's also one of the reasons why ice skaters spin faster as they bring their arms closer together. If you've ever seen that, ice figure skaters, they tend to do that a lot. They put their arms out, they slow down, and then when they bring it in closer, they speed up. So angular momentum has a lot of real life applications. Now, just like linear momentum, angular momentum is conserved, and so we tend to write it as L naught equals L. Easy peasy lemon squeezy. And just like with linear momentum, with angular momentum, we tend to have two objects. We can sometimes start with two momentums, and then we end with two momentums. Same thing's going to apply that we talked about in the linear case, where a lot of times you just want to try and draw a picture. There are times where two objects might start as one, like a person might be on top of a merry-go-round, and then the person jumps off the merry-go-round. That's essentially like an explosion. You might have a person jump onto a merry-go-round. That would be like a sticking scenario. Um, you could have something like a bat getting hit by a ball. That these are all different examples of these angular collisions going on. Right. One thing to keep in mind though is that a lot of times you might actually see problems where you have, I said it before about a person like jumping onto a merry-go-round or a ball coming in and hitting a bat. In a lot of those cases, the object, like the person and the ball, tend to have linear momentum. They're coming in a straight line. But the question is, how are we going to take that and incorporate it into an angular momentum problem? Because we can't just set the linear momentum of a person equal to the angular momentum of the system. So what we end up doing is we kind of like fudge stuff a little bit. It turns out that a particle that moves around in a circle will have a rotational inertia of mr squared. Now, even though the a person, well, we'll consider the person jumping onto a merry-go-round, even though the person may be running in a straight line, we can pretend as if it does. We can consider it as if it had angular momentum just from the very moment that it's about to collide. Because for the most part, we actually don't really know what happened before the collision, or at least everything that happened right before the collision doesn't really play a factor. What plays in the factor is the collision itself. So what we can say is that the angular momentum of the particle that might be moving in a straight line would be given as mvr, or its linear momentum times the radius. So this is how we're going to figure out or we're going to convert a person or object's linear momentum into angular momentum so that we can solve for the conservation of angular momentum. You're going to see a few practice problems both in this video and in class. So if it's still not sticking, uh, hopefully after you see a few examples, it will make a lot more sense. All right, so here's the first question. Pause the video work itself. Let me go over a second. All right, again, so this is perfect example of what I was talking about. It's asking, what happened? Why does the speed get greater as it gets closer? You'll see that there's one answer that says conservation energy, but wait a minute, it says kinetic energy. Again, this is how they kind of trick this type of question. They throw in something to make the energy answer wrong. Typically, if one of the answers talks about angular momentum, there's a very, very good chance that it's the answer. So that's why it's C, conservation of angular momentum. All right, here's the next question. Pause the video, work itself, and I'll go in a second. All right, so here's just another very typical question of kind of, what factors, 1-1 method type questions. First one asks, what factors does the angular momentum change? Well, we know that the angular momentum doesn't change. The person pulls their arms in. There's no outside forces, no external torques. Therefore, the momentum should remain conserved. It's not transferring this momentum to angular momentum to anything else. So the angular momentum doesn't change. There's no change in this, or you could say it changes by a factor of 1. Part B, what factors the angular speed change? Well, since the angular momentum doesn't change, if I use the equation L equals I omega, if the rotational inertia decreases by a factor of 2, according to that equation, I and omega have an inverse relationship. So angular speed should end up increasing by a factor of 2, or essentially getting doubled. And then the next question, what factor does the rotational kinetic energy change by? Well, we have to do the 1-1 method with the kinetic energy. The rotational inertia decreases by a factor of 2, while the angular speed increases by a factor of 2. That's being squared. Notice that I dropped the 1/2, because remember, whenever we do the 1-1 method, we don't care about any other terms except for the ones that are being changed, and constants get thrown out. So 1/2 times 2 squared gets me 2. So the kinetic, the rotational kinetic energy will increase by a factor of 2. Here's the next question. Pause the video, works up. I'll go over in a second. All right, so this is the type of question I was talking about before. We have a merry-go-round that's spinning around, and then a child kind of steps onto it. So they're kind of coming on without coming on with a speed. So the idea is that they're just kind of increasing the mass of or I shouldn't say mass. They're increasing the rotational inertia of the merry-go-round, and then we're going to try and figure out what happens to the angular speed. So what we're going to have to do is do conservation of angular momentum to figure out what the final velocity is going to be, or to find this ratio of initial to final, because we don't know what the initial angular speed is. The child initially has no angular momentum. Again, they're just kind of stepping onto it, so they're just adding onto it. And this is essentially kind of a sticking problem because we start with the merry-go-round moving, being the only one that's moving, and then the child goes on and is now going to rotate with the merry-go-round at the exact same rate. So the child gets stuck onto the merry-go-round essentially. The merry-go-round initially has this as the initial angular momentum, and then the final angular momentum will be the combined angular inertia, rotational inertias of the two people, the merry-go-round and the person, times its final angular speed. From here, now you can see how we're going to figure out the ratio without knowing either of the angular speeds, because we could just divide the initial angular momentum over to here, and then this total rotational inertia over to the other side. Well, we'll do it eventually. There we go. So we do it at the very end. We replace before we moved it over, we replaced the rotational inertia on the merry-go-round with 1/2 mr squared, and the child with mr squared. There's a r squared in all three terms, so we could drop them all out, and then we could multiply both sides by 2 in order to get rid of the 1/2, and then we would end up having the 2 on this side, and then we move it over to the other side. So this ends up being the final answer. The mass of the merry-go-round divided by the total mass of the system plus an extra mass of the child. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So here, this is kind of continuation of sort of a continuation of the problem. We have the child that's already on the merry-go-round, and then they end up moving towards the center of the merry-go-round. Now the question is, how does the angular momentum of the system change? Now, a lot of people will think that because there's no person or anything like that, they might think, okay, that the person's not leaving the merry-go-round and not acting perpendicular to the motion, or they're just kind of moving radially inward, that there must not be any change in the angular momentum. But that's not actually the case. Because if we think about it, uh, in this previous problem, we saw that the final angular momentum was the rotational inertia of both the merry-go-round and the child combined together. Now, the merry-go-round's radius and size don't change as the child moves inward, but the position, the R part, how far away the child is from the rotation, the axis of rotation, does change. So this term actually will go down. And if this term goes down, then the combined rotational inertia of the system goes down. And according to this, there's no outside torques, so the decrease in the rotational inertia of the system is essentially like uh, the figure skater pulling their arms in, and by doing that, decreasing the rotational inertia means that you're going to increase your angular speed. So I kind of actually answered both these questions. The angular momentum doesn't change because, again, there's no outside torques, there's no outside forces or anything like that that would result in a change in angular momentum. And the speed of the system will end up increasing because the child moving in closer decreases their rotational inertia, which therefore decreases the rotational inertia of the system. And because angular momentum must be conserved, the angular speed has to go up. Right? So a lot of times what you want to try to do with these questions, because they do this a lot, where they start asking about kids going in and out on merry-go-rounds, and a lot of people tend to struggle with it. You want to try and relate it to something similar. So, instead of thinking about the kid moving in the merry-go-round, think about a person pulling their arms in. We know what that scenario looks like. When a figure skater pulls their arms in, they start going faster. So the same thing's going to happen here. Just like how your arms, when you kind of have them out, they have mass outside it, and they change. They have their own kind of rotational inertia. You bring them in separately without changing your body, and all of a sudden the rotational inertia of the system will end up going down. So it works the exact same way as this merry-go-round setup. All right. Here's the last question. Pause the video, work yourself, and we'll go over to a second. All right. So we have the child now on the merry-go-round, but it's at rest. They're going to jump off. How are we going to find the final angular speed of the system? Well, again, this is essentially the explosion when two objects are initially at rest. So we know, we do conservation of angular momentum. The initial angular momentum 0, so that just tells us that the angular momentum of the merry-go-round and the angular momentum of the child will be equal. We can set the I omegas for both equal to each other, though we're just going to replace the I omega for the child with NVR. Again, this is kind of what we always do. That's how we take a linear setup and turn it into an angular momentum. Um, and then we know what the speed of the child is. So we just kind of move some terms around, try to get rid of some r's, solve for the angular speed of the merry-go-round, and we end up getting 0.9 radians per second.